Hello everyone, welcome back. So today we will discuss on carbonylation reactions. In the last class we were discussing the hydrogenation reactions, right? Today we'll basically try to introduce carbon monoxide into the organic molecule. How can one introduce this carbon monoxide into the molecule, and therefore the carbon count can go up by 1. So there are traditionally, as you can see, carbonylation method can be of few different types. One is Monsanto acetic acid, another could be hydroformylation, and of course hydrocarboxylation and so on. So first we would like to discuss the Monsanto acetic acid process, and that involves incorporation of carbon monoxide into the molecule, as you may know. So Monsanto acetic acid process. Monsanto acetic acid process is the conversion of methanol plus carbon monoxide into corresponding acetic acid, right. Now traditionally or historically rhodium catalyst has been used, but industrially nowadays iridium catalyst is used. You need also HI catalytic amount, and that reaction temperature is 180 degrees centigrade. Now this reaction is quite interesting, and it is done in industrial scale. As you can see, this is the industrial synthesis of acetic acid that we get. Now the starting material is methanol and carbon monoxide. How one can convert these two molecules into the acetic acid molecule. Also one thing to be noted, that rhodium or iridium catalyst can be used for this. Mechanism for both of these catalysts are exactly same, and most importantly you need catalytic amount of hydroiodic acid, that is HI. Let's try to look at the mechanism of this reaction. As you will see, whatever fundamental type of reaction we have discussed, it will come into play, and it will demonstrate that these organometallic reactions are nothing but governed or dominated by the fundamental reaction that we have mainly discussed for this course. Okay, let's look at the mechanism. Of course, the first step of the mechanism is conversion of methanol to methyl iodide with the help of HI. Right. So you convert methyl iodide plus water. Methanol is converted to methyl iodide and water. This is something you must remember. Without that the catalytic cycle cannot start. So methyl iodide formation is absolutely crucial. Now from there on, of course, a catalytic cycle will start off where rhodium will come into the picture. So that is rhodium CO dicarbonyl species, that's the catalyst, let's say, is used. It's a 16 electron species, and the methyl iodide that we have just converted will participate into the reaction and undergo oxidative addition, right. So methyl iodide oxidative addition will give you the carbon metal bond, carbon rhodium bond in this case, carbon monoxide and I3 minus. You started with 2 iodide and then you have one more iodide, so that makes it I3 minus. This is an 18 electron species. From there on you can undergo alpha migratory insertion. That is what we have studied. We have studied this oxidative addition, we have studied also this alpha migratory insertion. That means that where you will see that alkyl group will migrate into CO, that we have discussed again previously. So you will get acyl equivalent formation with a metal component being there. So one carbon monoxide is less now. So that carbon monoxide has been incorporated into this acyl component, and you have I3 minus, right. Now this is the alpha migratory insertion. So alkyl group has migrated to one of the carbon monoxide to form the acyl group. Now from there on we have this species 16 electron, right. If you count, so alpha migratory, so oxidative addition gives you 16 to 18 electron, 18 electron to 16 electron for alpha migratory insertion. Further you have now the carbon monoxide is interacting with the metal complex, and therefore, so these reactions are done under the carbon monoxide atmosphere, as we have discussed in the very first instance. Now we will have this 2 of the carbon monoxide, as you can imagine, one more carbon monoxide gets in, gives you the 18 electron species. So 16 to 18, 18 to 16, 16 to back to 18 electron species, and you have of course I3 minus. From there on, reductive elimination will give you the CH3COI. So that is coming from, so this acyl unit and one of these unit iodo will reductively eliminate, and therefore you will get the acyl iodide. So what we have seen in this particular species, it's basically dancing between 16 electron species and 18 electron species. Starting with the 16 electron species, we have seen the oxidative addition that gives you the 18 electron species. Now that 18 electron species can give you again the 16 electron species where alpha migratory insertion is going on. After that, you see 16 electron species again comes back to 18 electron species when carbon monoxide is interacting or coordinating with the rhodium center. Therefore, you get again back to the dicarbonyl species. Next, what is left to do is the reductive elimination, as we have seen that one of the iodide and the acyl unit, CH3CO unit, reductively eliminate to give you CH3COI. So essentially, we have seen oxidative addition, alpha migratory insertion, ligand coordination, that ligand is here carbon monoxide coordination, and reductive elimination. All these fundamental steps we have discussed earlier during this course. Okay. So as you see, all the organometallic reactions, the mechanism becomes very simple, and it's like the simplest you can perhaps imagine as you have some understanding of the fundamental steps. Without these fundamental steps, this understanding can be problematic. Therefore, the major activity or major focus of this course, as you have seen, has been the discussion of the fundamentals of organometallic chemistry or the steps, and therefore in organometallic chemistry almost any mechanism you can explain by these fundamental steps. Okay. Moving on from the CH3COI, of course you have this acyl iodide CH3COI. From there on you will see that the hydrolysis, okay, CH3COI hydrolysis, that is the last step of the reaction, can give you the acetic acid, right. So this is CH3, and acetic acid and hydroiodic acid back. So hydrolysis of this unit gives you acetic acid and HI back. Since it is producing HI, as you have seen in the very first instant, that HI is used as the catalytic amount. Okay, so your catalytic cycle will carry forward with little bit or tiny amount of hydroiodic acid. So the turnover limiting step for this reaction would be turnover limiting step would be the one where your rhodium and methyl iodide is both involved. So that means the oxidative addition is the rate determining step, and therefore you have the first order dependence with methyl iodide, first order dependence with the rhodium catalyst. So the first step, very first step, is the rate determining step. That's the slowest step. If you do the reaction with either with rhodium or iridium, both of them gives you the exactly same reaction mechanism. That means the first step is the rate determining step where oxidative addition into the methyl iodide is going on. At the beginning, you have seen the methanol conversion into methyl iodide, and over there you do not have too much of involvement of an organometallic intermediate. But once you form the methyl iodide, then you can take that one into the catalytic cycle where it interacts with the metal center to give you the oxidative addition, and that is turned out to be the rate determining step. Okay. Now we'll move on to the next topic, that is hydroformylation. It is of course the basic understanding will be similar to that of the just discussed reaction of the acetic acid process, but we need to briefly look at that and appreciate the steps of this transformation. Okay, so we are going to discuss the hydroformylation reaction. Hydroformylation, okay, as the name says it all. What we have in our hand is the conversion of olefin in presence of mixture of hydrogen and CO, and this is like 200 atmosphere pressure, usually industrially used, and you have a cobalt catalyst tetracarbonyl species, cobalt hydrido tetracarbonyl species, and you have the possibility of forming two products, okay, where the famous or most common this linear product, again one of the carbonyl and this hydrogen, two of the hydrogen, as you can hydride you can see, or the hydrogen atom equivalent you can see, carbonyl and hydrogen is getting into the olefin. Okay, starting from olefin you are going to get this product. So this is the olefin backbone, and hydride and CO is getting into it. So this is the linear product. It usually for this reaction, for this particular reaction, it is 4 equivalent, and the other branch product, so instead this aldehyde fragment can incorporate over here. So that means you will have this, COH and this H. Here of course you have again 2 hydrogen atoms and 1 carbonyl equivalent. So this is again the propene equivalent. From over there you have seen that aldehyde is getting into the branch position, or giving rise to the branch product. So this is so called the branch product. Starting from alkene you have the possibility of forming two products, that means linear and the branch product. Okay, so it's a hydrogen and CO mixture known as also syngas. Now this is the mixture reacting with the olefin to give you either terminal aldehyde or the branched aldehyde. What all you have introduced into the olefin is carbon monoxide and hydrogen or H2 equivalent, like 2 hydrogen atom, or you can say the 2 hydride equivalent you have introduced. That total unit, that aldehyde unit that is getting generated, if it is on a linear fashion, that's the linear product, and if that aldehyde is on the branch fashion or on the side, that is the branch product. And usually we see a 4:1 ratio, which is equivalent to roughly 1 kcal per mole energy difference for this linear to branch product. So getting selectively one of these product, completely selectively one of these product is going to be challenging. We will discuss more. But instead of the propene, let's say if you have styrene, then the scenario can be completely different, because the metal alkyl species that is getting generated can be stabilized, or the negative charge at the benzylic position will be stabilized, and therefore you may have the possibility of getting the branch product as the major product. But for the long chain olefin or aliphatic olefin, will usually get the linear product as the major product. Okay, let's look into the mechanism of these reactions. Hydroformylation. So mechanism of the hydroformylation reactions. Okay, so what you start with is tetracarbonyl hydrido cobalt species. Okay, HCO4. You do that quick electron count. It should be 18 electron count, and from there on you have one of the carbon monoxide is getting out. Of course, you need a 16 electron, so called little bit unsaturation is required, and you get to HCOCO3. This is a 16 electron species. From there on, you have the interaction of this alkene to give you HCOCO3 and alkene coordinated intermediate. Of course, this is going to be the 18 electron species. So 18 electron goes to 16 electron, goes to 18 electron. This is the olefin coordination, or so called ligand coordination, you can say. Now from there on, as you can imagine, you have the hydride equivalent and you have the olefin. So beta migratory insertion can take place. You should be very good at these things and understanding that this is the ensuing step that's going to predominate or will take over. So from 18 electron to, of course, you are going to get a 16 electron intermediate with the hydride at the alpha beta position. That's why it is beta migratory insertion into the olefin, and this is, of course, is going to be the major product. Of course, this is the one which is going to give you the linear aldehyde, right? Of course, there is a formation of the other one, which is the branch product, but that is going to be the minor one. So 18 goes to 16, 16 goes to 18, 18 goes to 16. So ligand dissociation, ligand association, or olefin interaction, olefin coordination, beta migratory insertion, that's the major step, or major product, and from there on you can see the alpha migratory insertion. So the whole alkyl group now will migrate into the carbon monoxide. So alpha migratory insertion will give you the cobalt species carbonyl acyl intermediate, okay, alkyl intermediate. So this whole alkyl group has transferred to one of the carbon monoxide. Of course, the 16 electron species you do have, and then from there on this process is occurring. From there on, what you will see is the interaction of hydrogen. I'm not going to write down the steps here. We'll discuss this in detail a little bit, and overall you will get the hydroformylation, that is the linear product formation. Okay. So this is very important to understand that this is a completely electron withdrawing or electron deficient intermediate. You have 3 of the carbonyl and 1 of the acyl unit. So all the ligands are electron withdrawing, and so oxidative addition will be difficult, right, into the hydrogen. So what you have seen here is the cobalt complex gives rise to an intermediate which is completely electron deficient. As you know, for oxidative addition, you need to have a very electron rich metal center. In this case, it is very electron poor. Therefore, we have given this question mark. What is happening in there? What will be the mechanism of incorporation of this hydride equivalent into this molecule to give you the long chain aldehyde? Okay. Now, if you again look back at this mechanism very carefully and simply, you would appreciate that all the steps involved in this process are very simple. You start with an 18 electron species. Of course, have to loosen up a little bit. From 18 electron species, you give rise to the 16 electron species, and then olefin coordination occurs to give you the 18 electron species back, and then you have the opportunity to do the beta migratory insertion to form the alkyl intermediate, metal alkyl intermediate. From there on, alpha migratory insertion can go on, and finally you get an intermediate which is highly electron deficient, but you have not introduced the hydride equivalent yet, or the hydrogen gas didn't interact yet. So therefore, from this highly electron deficient intermediate, if you have to incorporate hydrogen, what would be the mechanism? That's the one thing we need to look at it carefully. But nonetheless, as you have seen, from olefin we get the aldehyde. It could be either terminal or an internal one, so-called linear, and the branched one. And for aliphatic case, linear product predominate, as you may see later on, that for benzene ring containing one, or the let's say styrene or vinyl naphthalene cases, you will see the branch product will predominate, because that intermediate metal alkyl or metal alkyl intermediate, or that will be stabilized by the electron withdrawing effect of the benzene ring. In the case of alkyl group, you have an electron rich alkyl group. Therefore, the other product predominates. Okay, let's look back. Let's look back at that step where hydrogen was reacting with your acyl intermediate. Okay. So the last step, we are going to discuss the last step. So, mechanism 1, the first type of mechanism would be the one where we have the oxidative addition. Of course, that is one of the usual suspect. We think that there would be an oxidative addition, right, and that will give rise from 16 electron to 18 electron species and CO3 COR. From here, of course, you can get R, sorry, this is R, we are not drawing the R, RCHO and HCOCO3, that is your catalytic component, right? 16 electron species you may get. Now, the finally another mechanism is mechanism 2, that is the sigma bond metathesis, right? So, as we are saying that this mechanism will be unfavorable because of the fact that this is highly electron deficient intermediate. Further, if you do the computational chemistry or DFT studies, you will find that this is very high energy demanding. So, therefore, this one by virtue of its electron deficient character and also supported by the DFT studies or computational studies, that this is going to be highly energy demanding. Sigma bond metathesis is, I guess, the one as you have seen previously, when oxidative addition is not going to be a preferred pathway, sigma bond metathesis will be, and in this case it will be the case most likely, although direct evidence is lacking. You will have this coordination. With coordination, it's a four-centered mechanism. It will occur. So that means this one, 2, 1, 2, 3, and 4. This four-centered mechanism will give rise to the product formation, the same product formation you will get. So 16 electron species goes to 18 electron, back to 16 electron. Okay. So to sum up, we have seen the incorporation of carbon monoxide into the olefin. Two different processes we have seen today. One is the Monsanto acetic acid process, where from olefin or from propene we have seen the different product formation, and for specifically for from propene in this case carbonyl equivalent formation, we have seen the branch product formation and the linear product formation. For alkyl, linear product is the major one, and for the last reaction we were trying to debate between the oxidative addition and sigma bond metathesis, and we kind of concluded that sigma bond metathesis will be the one which will perhaps happen, basically because of the fact that oxidative addition requires the electron richness of the metal center, which is missing in this case of having highly electron withdrawing equivalent, and therefore the alternative one, that is sigma bond metathesis, will predominate or will pick up and give you the product. Okay, with that we'll close today's session, and I would like you to request to study this part more carefully and understand that these are nothing but the discussion of the fundamental steps that we have seen in earlier cases. Okay, with that, see you in the next one.